This was the last slide. We talked about the case X and case Z, and we saw that these are kind of useful if you want to read. On the left-hand side here you, oh, this is really slow. You can reduce the number of lines of code by putting X's in the left side of the case X or case Z command, or you can put them in the right side if you want. What do we call these? Don't cares, right? These aren't don't knows. These are the don't cares that we want to deal with, right? And you put them over here, it's like in the kernel map. You can simplify the kernel map or simplify the amount of logic. So that's the last thing we covered. A little bit. Negative numbers. Integers are 2's complement in Verilog. And if you declare an integer, it's a 32-bit value. The compiler eventually decides how many bits to use. Reg numbers are non-zero integers. So the length of the reg number is given by the declaration. So here's some example code. It says integer BC. So these are 32-bit values. There's a 5-bit register X. Always at BC or X says begin. It says X equals minus 5-bit decimal 6. So this will be stored as a 2's complement value. And X is 5 bits, so it takes the 5 bits. 2's complement inverts all the signals, adds 1. So that's what gets stored when you make a minus value for a register. B is 10, which is an integer, and C, which is also an integer, is B plus X. It'll take the B value, which is this 10, which is a 32-bit value. It adds it to this 2's complement value of the register, and we get this number 35. So yeah, you got to keep track of the fact that it's doing 2's complement in there. So you might have thought that was a 35 instead of a 3, but that's the way it handles negative numbers. The key thing to remember about 2's complement or about negative numbers, to change a binary number to 2's complement, yeah, this just shows how you do invert and add 1. The key thing is that when you add numbers that are negative numbers, you have to sign extend the numbers. So numbers that are of different lengths must be sign extended. So say you have a register X, which is 5 bits, and a register Y and Z, which are 6 bits. If I want to say Z equals X plus Y, I have to sign extend X to make it the same size as the Y and the Z. So to sign extend, you take the MSB and duplicate it. So in this case, the MSB was bit 4. I make it bit 4 again. I make a new bus that's 5 bits, which has the sign extended version plus the other bits of X, add it to Y, and then add it. And that handles the negative numbers correctly. Okay, we're not going to be using negative numbers, I don't think, in this class, but just be aware of that. Fixed point calculations. Often when you're given a problem, you'll have an idea. You'll do something in floating point. You might do this in MATLAB or Simulink or some other thing. But then when you want to go into Verilog, floating point is very expensive to build floating point hardware. So we almost use what is called fixed point algorithms or fixed point hardware. So we're just doing adders and subtractors that don't have, a floating point has a mantissa and an exponent. We don't use exponent in fixed point. So the trick about doing a fixed point is that we have to figure out the fixed point has a sign, it has an integer part, and it has a floating or fractional part. So you have to decide how big is the integer part, that gives you the range, and how big is the fractional part, that gives you the accuracy. And so again, we're not going to do much about this, but there's a lot of work goes into figuring out how do you build things in Verilog to do algorithms, especially digital signal processing and converting things from floating point to fixed point and actually generating the hardware. And usually there's an optimum sort of trade-off here about how many the word length in terms of how many integer and how much fractional bits do you need. You can use for loops for building iterative hardware. So for instance, here's an example of a ripple adder. This is a 5-bit ripple adder. Instead of what we've learned already is I could make a ripple adder and then I could call it 5 times, but you can also use a for loop. And so here's an example of a for loop. It says always at C in A or B, begin C equals C in. And then it does this for loop for 0 to 5 or 0 to 4. It says C of SI equals A of I plus B of I. So basically, this little loop here is building all 5 of these things. So that's kind of convenient. for building, especially a large amount of hardware that you have to build. We don't use them too often, but just be aware that they exist. This next part's kind of important. So here's an example of some verilog. It says if, and we got some Boolean expression, could be A equals B or something. I don't know, some expression here. It says R equals A plus B, else R equals A plus C. And below here, I have two implementations of this verilog, okay? On the bottom one, it says, okay, it takes A and B and adds them together, and it takes C and A and adds them together, and then it has a little multiplexer. And the multiplexer is controlled by this Boolean expression. If it's true, then this path comes through, right? And if it's false, then this path comes through. And this is the logic that generates the Boolean expression. And you could see that if I were to figure out the worst case delay of this, I would say, well, it definitely has to go through an adder, and it definitely has to go through, or it can go through either an adder and a mux would be the worst case path, or this Boolean expression in the mux. So the worst case delay, hold a second, wife downstairs. Sorry about that. So what's the maximum delay of the circuitry? It's going to be the maximum of either the adder or the Boolean expression. So either one of these adders or this Boolean expression is going to be longer delay. So it takes the maximum of those, and then we have to go through the delay of the T-mux, or the time delay through the mux, okay? So that's the worst case delay of the circuit. On the right, this does the exact same function. It has a Boolean expression, and then it goes into the mux, and then we only use one adder. And the idea here is that we decide on B or C, and then pass that into the adder. A is added with either the B or the C. So in this case, the worst case delay is the Boolean delay plus the mux delay plus the adder delay. So you can see this has a longer delay. It's got all three of them. This just has either the adder in the mux or the Boolean expression in the mux. So this one on the left is faster, and this one on the right is slower. However, the one on the left takes more hardware, because here I had two adders, and adders are pretty expensive in the amount of hardware. Here I only had one adder, a mux, and a Boolean expression. So the one on the left faster, but more hardware, because basically we built a bunch of parallel hardware to calculate things in parallel and then just decide. So this is a very common thing you'll see in hardware. You know, if you want to go fast, you try to parallelize the hardware as much as you can to speed things up. The trade-off is there's more area, more power, more cost, okay? For us, fortunately, the synthesizer can normally figure this stuff out for us, okay? When you do a synthesis, what it's doing is you're specifying a speed for the synthesis. And when you specify a speed, it says, oh, if I need to go fast, if I don't have to go fast, it would do something like this. Let's just minimize the area. It's fast enough. As you say, I want to go faster. And by fast, like in your labs, say you have a 5 megahertz or a 10 megahertz clock, it's deciding how to arrange this logic to go at that speed. If you speed that up, as you start speeding it up, it starts doing things like this, adding more parallel hardware to speed it up to meet your speed requirements, okay? So the synthesizer normally figures this out for you, thankfully, but it's kind of cool that it figures this all out, maximizes the speed versus the hardware. So this is optimizing for the right on area, optimizing on the left for speed. Any questions about that? Oh, somebody said, is our midterm mark posted under the assembly? Oh, yeah, next thing about FPGAs, there's a couple of things to keep in mind here.